Hello, everybody. Welcome to today's lecture. So today we're going to get into 6.4. Just as a reminder, 6.3, we talked about Euler circuits and Euler paths. Okay. So these were paths or circuits where you only cross each edge one time. Okay. Like here you can see we only cross the edge AB one time, only BE one time, etc. Now, one key thing that we needed to utilize a lot was that we could go to any of the vertices more than once, right? Like we went to A 3 times, we went to B 2 times, we went to C 2 times, we went to E several times. Well, just three, I guess. But so we had to go to vertices more than once, many times. Today we're going to talk about a type of path where we only go to each vertex one time. Okay. So these are called Hamiltonian circuits or Hamilton circuits. Okay. The book kind of uses two different names for them. The section is called Hamiltonian circuits. The definitions are called Hamilton circuits. So I'll just go with Hamilton since that's what it is mostly referred to. Okay. So, whoops. Let me get a different color here. So this section is called Hamilton circuits. Okay. So just a little bit of introduction here. The type of problem that we want to solve is often referred to as the traveling salesman problem. The traveling salesman problem. Okay. Or TSP. Now let's think about like what this would mean. Well, if you were a traveling salesperson, you would only, if we think about like the vertices, okay. So if you have like some kind of network like this, right? You would only want it if the vertices here are like houses that you're traveling to, you'd only want to hit each house once. Right? There's no reason you'd want to go to any of the houses more than once because you've already been there, right? So you either made the sale or you didn't. There's no reason to go back to the house. So that's kind of our motivation here. We want to only touch each vertex one time. But anyway, the traveling salesman problem, it's defined as any problem where you must visit every vertex of a weighted graph once and only once, and then end up back at the starting vertex. Okay, that's where we get the circuit part of this from. Okay. So the word weighted in the weighted graph, that just means that it has numbers on it. If it doesn't have numbers, that's fine too. Like the one I just drew here doesn't have numbers. But it's just referring to something like, if you remember back in 6.3, or was it 6.2? Yeah. Back in 6.2 here, where we had the numbers on the graphs, that's all it means by weighted graph. Okay, but if it doesn't have weights, that's fine too. It works just the same. So the traveling salesman problem, it's not just about salesmen. It could be applied to a lot of things like delivering packages. Some of the other ones it gives are circuit boards, scheduling jobs in a machine, and running errands around town. Okay, just any time where you want to visit every vertex once and only once, and you want to start back at the starting vertex, right? So maybe like the starting vertex is your house. So you want to start at your house, go to every like in the if you're a salesperson, every house you want to sell to, and then back to your house. Okay. So let's start with the definition of a Hamilton circuit, which is basically this. A Hamilton circuit is a circuit, meaning we start and end at the same vertex, that must pass through let me that must pass through each vertex of a graph once and only once. Okay. So at first glance, this is harder to accomplish than an Euler circuit, right? Because with an Euler circuit, we had to often use the same vertex many times. So this will be a bit more limited than that. Remember, in our initial definition of a circuit, it still has to follow the same definition of a circuit because it is a circuit. If we go back to our initial definition of a circuit, it's a path. And if we go back to our definition of a path, it travels over any edge only one time. Okay. So now with the Euler circuit, we could travel over the edge only one time. But with the Hamilton circuit, we also have to travel through the vertex only one time, right? So just go back here. So with the Euler path, it has to travel through every edge, right? With the Hamilton path, we don't have to travel through every single edge, but we still can't use an edge more than one time, and we have to pass through every circuit or every vertex only one time. So we have a lot more restrictions here. Okay. But the one thing we don't have to do is use every single edge. So maybe there's an extra one that we don't have to use. Okay, that's the only really bit of leeway we have. I'll give you some examples in a second here. Let me write down, related to this, a Hamilton path. Well, you can just think of the difference between a path and a circuit in general. But a Hamilton path is a path that same thing must pass through each vertex. Sorry. Must pass through each vertex of a graph once and only once. Okay. So let's just start with the simple example. This one's just from the book here. Whoops. Okay, so this is figure 6.4.1 from the book. We have A, B, C, D, and E. And then we have this edge, this one. Nope, never mind, we don't have that one. We have this one, this one, this one, and this one. Okay. So can we find a Hamilton path that goes through here, and then can we find a Hamilton circuit that goes through here? Well, just like with the Euler paths and Euler circuits, we will have algorithms to do this. But for now, let's just try it. Okay, so if we start at A for a path, let's say we go down to E, up to B, down to D, and up to C. Okay, so it's pretty straightforward. You just basically try it, and it works out pretty nicely for this one, just because it's set up to work nicely. So we have A, E, B, D, C. And if we want to make it a circuit, we can use that edge AC to just go back. Right? So A, E, B, D, C, A. Okay. So nothing too bad on this one. But some of them are a little bit more difficult. Like if you look at in that same figure, part B and part C are both more difficult. B doesn't actually have any circuits. They're pretty big though. I won't write those down. We'll have plenty of examples throughout this lecture. But those are good ones to look at if you want another one right now. Okay, right now, but what's important right now is that you have this concept down, okay? That we want to hit every vertex only one time. And just like before, we can still only use the edges one time as well. That's always a rule. Okay. So another definition now, a complete graph is a graph with n vertices. So n could be whatever number, like in the graph we have up there, it's 5, right? We have 5 vertices. In which every pair, every pair of vertices is joined by exactly one edge. And that's it, actually. So it's a graph with n vertices in which every pair of vertices is joined by exactly one edge. So if we went back up to this one, is this the case? Well, A and C are only joined by AC, A and E are only joined by AE, etc. Okay. Now, what about the fact that let me think. With this one, every pair of vertices has to be joined by exactly one edge. So AE only have one edge, right? AC only have one edge. But what about AB? Well, there's 0 edges here, right? A and B are not joined. So same with A and D. So this one's actually not a complete graph. You need to have one edge linking every pair of vertices exactly one time. Okay. So this one would not be a complete graph up here. The notation for a complete graph, by the way, is K with N as a subscript. Okay, so it looks like K sub N. So, for example, K2 is a complete graph with 2 vertices. And we're giving it this specific name because there's really only one form it can take. It's going to look like this. Okay. There's not really a different way you can draw it. Maybe you could draw it like vertically or diagonally, but ultimately it's the same thing. So we give it a unique name, K2. What's K3 going to be? Well, it's just going to be a triangle. Okay. So every pair of edges here is joined exactly once. K4 is a little more challenging. Naturally, we might think to draw a square next. And that's a good starting point. Square or a rectangle, doesn't matter. So we have this, but let's give them some names just so we can talk about them here. A and C aren't joined by any edge, so we need to add an edge there to join them. And B and D aren't joined by any edge, so we need to add an edge there to join them. Okay. K5, maybe we could look at this one up here and try to complete it. Let's see. Whoops. My bad. It's fine. I'll just redraw it here. K5. So we had A, B, C, E, and D. And then it looked like this. Okay. And I talked about what made it not complete. Right. And so let's take all the reasons it's not complete and try to make up for those. Okay. So A needs to be connected to D, first of all. And it needs to be connected to B. Okay. So far, so good. A is connected to every vertex now, exactly one time. So let's go over to B. B is only missing a connection to C, so let's add that in. Okay. Now C is only missing a connection to E, so we'll add that in. D is connected to everything except E, and now E is connected to everything. So this is what it would look like. It has like a star in the middle. I didn't draw it too well. Maybe I can do a little better of a job underneath it here if I do it from scratch. So we have like a pentagon and then like a star in the middle. Okay. And not too much better, but a tiny bit better. So these are the vertices on the corners here. So this is what the complete graph with 5 vertices looks like. So notice like as we go down the line, we're getting more and more edges. Here we have 1, here we have 3, here we have was it 1, 2, 3, 4, 5, 6. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? I feel like maybe I missed some. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's hard to keep track of them all. I think there's 10 though. Okay, so the point is though, as we go down, we're gonna have more and more edges, so I won't draw all of them here. This is what it looks like up to 5. This is all the book shows too. Yeah, and it does say it has 10 edges. So there we go. Um, So one thing that the book notes, which will tie into some of our theorems later, complete graphs cannot have Hamiltonian circuits. Okay. It could possibly have a path, but it cannot have a Hamiltonian circuit. Okay. Um, oh, I'm sorry. I think I had that backwards. Yeah, never mind. Sorry. Complete graphs do have Hamiltonian circuits or Hamilton circuits. Um, sorry. Yeah. Yeah, they definitely have Hamilton circuits. We can just tell just by looking at it. Like K2, for example, if you want to touch both vertices, well, you just start here, go across here, end here. That's a Hamilton circuit, or, well, it's a Hamilton path. Um, so this one, it can't have a circuit because it only has one edge. But here, you can have a circuit, right? You start here, go here, back here. An easy Hamilton circuit. So you can have Hamilton circuits in these. In fact, I think it would be pretty common for all of them. I think above K2, like K3 and on, it's pretty easy to get a Hamilton circuit because you can just go around the outside, right? You could go A, B, C, D. Remember, you don't have to use every edge. We could do A, B, C, D, E, A, and then we have a Hamilton circuit. So yeah, they do have Hamilton circuits. I was mixed up the first time there. And because they have circuits, that means they also have paths because you could just not go over that last edge and then you have a path, right? One more definition. A reference point is the starting point of a Hamilton circuit. Okay. So it's the starting point of a Hamilton circuit. So, like, if we start at A here, then A would be the reference point. So you could have any of them be the reference point. It doesn't really matter. So I've said, in K3, for example, if you start here, go here, back to here, that's a Hamilton circuit. But we could also, we could go in like the opposite direction. That would also be a Hamilton circuit. So one question is how do we know how many unique circuits we have? Okay. So the number of Hamilton circuits. Okay. A complete graph with n vertices is n minus 1 factorial. So this exclamation point is what's called a factorial, which I'll explain in 1 second once I finish this. Is n minus 1 factorial Hamilton circuits. Also, since half of these are mirror images of each other, so like what I said with the triangle one, how we could just go in the opposite direction. there are only half as many unique circuits. Okay. So this is something we didn't really have before with the Euler circuits. It was a formula to find how many there are. So to summarize here, okay, there are n minus 1 factorial divided by 2 unique Hamilton circuits in a complete graph. Okay. So, I mean, this is pretty limited because we're only talking about complete graphs, which oftentimes we wouldn't have. But it's a good starting place still. There's n minus 1 factorial unique Hamilton circuits, or n minus 1 factorial divided by 2 unique Hamilton circuits in a complete graph. So before we go further into here, we need to know what this exclamation point means. What does factorial mean? So let's write this as an aside. The book doesn't explain it here because the book explains it earlier. Okay. But a factorial, or n factorial, is read as n factorial. Okay. It means actually, let me just write equals. So the formula for this n factorial is equal to n times n minus 1 times n minus 2 all the way down to 1. So you take the number and you multiply it by every number smaller than it. So 5 factorial is 5 times 4 times 3 times 2 times 1. Okay. So it's that number multiplied by every number smaller than it. So this ends up being 120. 4 factorial is 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. 1 factorial is just 1. And we also define 0 factorial to be 1 as well. Okay. So, if you don't want to calculate this, you could just put like six exclamation point into Google and it'll just spit out the number. Like 6 factorial would be 6 times all of these numbers. So 6 times 120 is 720. So these numbers get big really fast. And what the factorial tells you is how many different ways you can arrange that number of objects. So if we have 3 objects, there's 6 different ways we can arrange them. If we have 2 objects, there's 2 different ways we can arrange them, right? You have 1, 2, or you could do 2, 1. Okay. So this is the information it's telling us. So naturally it would come up here because we're talking about how many different ways we can arrange the vertices, essentially. So let's think about the triangle graph, okay? How many unique Hamilton circuits are in the K3, the triangle graph? Well, there should be 3 minus 1 factorial divided by 2. Okay, 3 minus 1 is 2. 2 factorial is 2. 2 divided by 2 is 1. So there's actually only one unique Hamilton circuit. Because if you start here, go here, back to here, well, if you do a different circuit, it's just either going to be rotating that one, so it's really going to be the same circuit, or it's going to be going the opposite direction, which again is really the same circuit. Okay. This also kind of explains why there's not one for K2. I mean, it's obvious why there's not one, because once we leave, there's no way to get back. But if we put it into the formula, 2 minus 1 factorial divided by 2 is 1/2. So this tells us there's half of a Hamilton circuit, but that doesn't really make any sense, right? So we either have to conclude the formula is not true, or that K2 just doesn't have any, which is what the case is here. Let's think about K4. There should be 4 minus 1 factorial divided by 2. 4 minus 1 is 3. 3 factorial is 6. So there should be 3 unique Hamilton circuits here. So there's A, B, C, D, and all the variations of that, right? Like A, D, C, B, or B, C, D, A, B. That's one circuit. Then we can also utilize the edges here. We could go A, C, D, B. That would be a unique circuit. And we could go A, B, D, C. Okay. And that would be a unique circuit too. So I think that's going to be all 3 of them. What about K5? Well, it's going to be a lot harder to find these ones because there's going to be a lot of them, right? We're going to have 5 minus 1 factorial over 2. So this is 4 factorial over 2. 4 factorial we found is 24. So there's 12 different circuits. Okay, so there's going to be a lot of them here. So I won't bother finding them all. But you can see they're just going to get bigger and bigger as you go up. Once you get to K6, now you have 60 of them, right? So it's a lot more. Once you go to K7, then you have 720 divided by 2, whatever that is, right? Like 360. So there's a lot of them. Okay, so let's go back to the traveling salesman problem. Remember, the traveling salesman problems, they typically, it said, involve weighted graphs. They don't have to, but they typically do. We haven't had weights here, but with a weighted graph, we typically, we want to visit every vertex, but we also want to do it in the most efficient way, meaning with the least cost. So how do we solve those problems? Okay, if we can find the Hamilton circuit, how do we know which of them, like if there's 3 of them, for example, which of them is the cheapest? Whatever that means, like costs the least amount of money, takes the least amount of time, takes the least amount of distance, whatever it is. There's a couple ways we could do it. So solving TSPs, traveling salesman problems. So from now on, we'll always have a weighted graph. So we'll have numbers on each of the edges, okay, giving it weight. So the first algorithm is called the brute force algorithm. Okay. So we just brute force it. We just look, okay, here's all the Hamilton circuits we could have, and this one costs the least. Okay, so we just list all the possible Hamilton circuits, and then we look at the cost of all of them. So let's give an example. Well, first let's write that down, right? So first, we list all possible Hamilton circuits. Okay. So the traveling salesman problems are just finding Hamilton circuits. The only difference is they typically have the weights on them. So we need to find first the Hamilton circuits. So we list all the possible ones. Still not the easiest thing to do because we don't even necessarily know how to find them other than just guessing and checking. right? So this might not be the best algorithm, especially if we have a lot of them. Like for example, on K5, we have 12 of them. That's going to take a long time, right? Maybe for K4 and under, it would be fine. B, for each circuit, find the total weight. Okay. So then the one with the least weight is the winner. Okay. So let's look at this example that they give in the book. Okay. So we have A, B, C, D. Okay. Actually, B and C are switched. So we have this, and then we also have some weights. We have this one is 8. Let's think about this as like miles, I guess, right? So the weights are miles. So we have 8 miles from A to C, 6 miles from A to D, 4 miles from A to B. So obviously this isn't to scale. 3 miles from B to D, 5 from D to C, and 3 miles from B to C. Okay. So we want to find the most efficient circuit. So we want to start at, say, A and end at A. It doesn't actually matter which one we start at, though. And we want to find the optimal path where we touch every vertex one time. Okay. So first, let's think about how many Hamilton circuits there's going to be, right? Is this a complete graph? We sure hope so, because otherwise we don't have a formula to find out how many there are. But it is a complete graph, because if you look at every vertex, they're all connected to each other one time. So this is actually K4. It's just drawn differently. Okay, it doesn't always have to be drawn the exact same way. It's equivalent. Okay. So this is a complete graph. By the way, let me write example here. This is a complete graph. And there's 4 vertices. So there are 4 minus 1 factorial divided by 2 different Hamilton circuits. So that's 3 factorial over 2, which is 6 divided by 2, which is 3. Okay. Again, for the factorial, you're really only usually using like the first 5 or 6 numbers. So you could just either memorize the numbers. A lot of calculators will have the exclamation point button, or you can just literally type into Google like 3 exclamation point and it'll just give you 6. Okay. Or you could just do the multiplication by hand, because for some of the smaller numbers like 3, it's not so bad. Because you're just doing 3 times 2, essentially. So there's going to be 3 Hamilton circuits here. So for the brute force method, we need to list them. So we're going to list the Hamilton circuit and then list its total weight. Okay. And we should have 3. So the easy one is like where we just go along the outside, right? We could do A, B, sorry. I meant to A, C, B, D back to A. Okay, so that would be one Hamilton circuit. We're using every vertex one time. So let's list the total weight here. When we go A to C, that's 8. C to B, that's 3. B to D is 3, and then back to A is 6. So we have 11, 14, 20. Okay. Now you have to find the other Hamilton circuit. So this is where this algorithm falls short, is that it relies on you finding the circuits by hand without really any guidance. With the Euler circuits, we had a way to do it, but here we don't really. So let's just find, let's try to find a different one. We don't want to do one that's like backwards or something like that, like the same thing. Let's do A, C, D, B, A. That would be different, right? If we start at A, still go up to C, but now we go down to D, then to B, then back to A. That one would be different. Okay. So we'd have 8 plus 5 plus 3 plus 4. 8 plus 5 is 13, plus 3 is 16, plus 4 is 20. Okay, so we got the same thing for the weight. So these paths are different, but in terms of the distance, it takes the same amount of miles to travel them. So there should be one more path here. Let's try to find it. Try not to use the book here so you can see how to do it. You just kind of got to stare at it for a while. So we already did ACB, ACD. Whoops. What about... See, things like A, B, C, D, A. Well, yeah, okay. We could do A, D, C, B, A. Or how about this? A, D. No, that would be the same. All right, what about A, D, C, B, A? Is that different? A, D, C, B, A. So when we're trying to figure out if it's different, first we need to check it's not just one of them backwards, because that wouldn't be different. And second, that it's not one of them rotated, meaning like we just start in a different place, right? Do any of these have the same order? It doesn't look like it, either backwards or forward, right? This one is different backwards and forward. This one's different backwards and forwards. I think this one's different. Let's add up the weights. 6 plus 5 plus BC is 3 plus 4. So 6 plus 5 is 11, plus 3 is 14, plus 4 is 18. So yeah, this is definitely different because we get a different number here. So yeah, these would be all three of them. But I mean, you can see the drawback already. I was struggling there to find what that last one is, and we were only looking at 3 here. What if we were looking at 12? That would be like impossible to find all of those by hand, right? You really have to be meticulous here to make sure that you're not doing the same one twice. Okay. So the book has them listed. They should be the same as ours, but it also has 18 as the best one. So this is the optimal path right here. Okay. This is optimal. But man, that's not a nice algorithm, right? Like if we only have 2, or if we only had like 3 vertices, maybe that would be fine. I mean, well, in that case, there's only one optimal path. This is pretty much the cutoff where it's reasonable, is when we only have 3 Hamilton circuits. And even then, it was pretty difficult. If we have more than this, it's going to be it's going to be way too hard to do by hand. So let's look for a different method. We actually have, I think, 4. Let me make sure I counted right. Yeah, it looks like there's actually 4 methods. So there's a lot of choices on this one. Let's look at the second method. The second one is called the nearest neighbor algorithm. Okay. Nearest neighbor algorithm. So you can kind of tell what you're going to be doing by the name here. You're going to be going to the nearest neighbor, but how exactly does it work? Okay. So first we want to pick a vertex as the starting point. Then we want to go down the edge with the smallest weight. Okay. So we go down the edge with the smallest weight. If there's more than one, just choose one. It doesn't matter. Okay. C, just continue building the circuit. And D, return to the starting point. Okay. So, I mean, it sounds easy enough. You just basically start with the one with the smallest weight and then just continue on from there, making sure you're following the rules of like only hitting every vertex once and only using every edge once. So let's use this on this graph right here. Let me just copy and paste it. Okay. So we want to pick a vertex as a starting point. I like to use A. Okay. So we'll start at A here. Now we want to go down the shortest path, which is from A to B. Okay. So we did A to B. Now we just want to keep going. So going to C or going to D, it doesn't really matter because they both have the same weight and they'll both follow the rules. Whoops. Sorry. So let's go I don't think it matters here. Let's just go to C. Now we need to hit D, so we have to go down to D. And then we got to go back to A. Okay. So what weight did that leave us with? We have 4 plus 3 plus 5 plus 6. So 7 plus 11 is 18. Okay, so it works. Essentially, you just start with the smallest one and then just go from there, and it ended up working here. Okay. If we would have went to D instead first, like if we would have went this way instead of going this way, let's see, it would have ended up being 4 plus 3 plus 5 plus 8, which would have left us with 20. So it's not, let me make sure that's right. 4 plus 3 plus 5 plus 8. Yeah, so it would have left us with 20. So it's not foolproof. Okay. So the thing with the nearest neighbor method is that it will give you an efficient path. It just might not give you the optimal path every time. Here it did, but if we would have made the choice to go to D instead of going to C first, we would have ended up with 20, which is efficient. It's not that much further, right? It's only like 2 miles further, but it's not optimal. Okay, so it doesn't always necessarily give you the optimal path, but it will give you a good path. Okay, and it's pretty easy to follow because you just pick the shortest one. All right. The third algorithm is pretty much the same thing. It's called the repetitive nearest neighbor algorithm. Okay. So it's pretty much just doing the nearest neighbor algorithm, but using different vertices as your starting point. Okay. So pick a starting vertex. Apply the nearest neighbor algorithm. Okay, so that was the last one we did. Then pick a different starting vertex. And then 4, just repeat. Okay. Repeat step 2. And then you just keep doing it, right? Then you pick another one, and then you repeat step 2 again. And you, like, basically what's happening here is, okay, the nearest neighbor algorithm, it gives you an efficient path that might not be the optimal one. The idea is if we do it a few times, then we have a better chance of finding the optimal one, or at least a more efficient one. So here we start at A, and we do our path, and now we say, okay, let's try it with starting at B, and then we do a different path. So if we start at B, we'd have to go either to D or C, and then we'd get 2 different paths that way. And then we try it starting at C, right? So we start at C and we go to B, and then we have to pick between A and D, etc. It's basically just giving you a larger sample size so that because there's some randomness to this, it's more likely that you'll pick the optimal path. So I won't do an example of this because it's not really too necessary most of the time. As long as you know how to do the nearest neighbor one, that's fine. This one's just doing the nearest neighbor one more than once. There might be a homework problem with this, but again, it's just doing the nearest neighbor one more than one time. Okay. So you just pick one to start with, do it, pick a different one to start with, do it, and then just see which one is shorter. Okay. And there's no like hard number of how many times you have to do it, just however many seems appropriate. If you think you get a good efficient path, then you could just stop there. Let's look at the last algorithm. This one's more unique than the last one. This one's called the cheapest link algorithm. So with the nearest neighbor, we pick a starting vertex and then go the shortest distance from there. With this one, we instead want to look at what's the shortest distance on the graph. So we're not picking a vertex first. We're just looking at um we're just looking at the different distances and looking at what's the shortest one. Okay. So pick the link with the smallest weight. Okay. Again, if there's a tie, just pick one at random. Pick the next smallest weight. Okay. Keep doing this. But you have to avoid closing the circuit. Okay, so if there's one that's going to close the circuit too early, then don't pick that one, pick the next one. Okay, and I mean that's it. Okay. So you just keep doing that till it's done. Let me grab this one again. I think I actually already have it copied. All right? Maybe not. Let me grab this. Okay, so we want to take the smallest link. We have a tie here though. We have BD and BC. They both have 3. So let's take BD. Now, the next smallest one is BD. So let's take that one. The next smallest, now I missed one thing in the steps here actually. So for step 3, we want to keep doing this, avoiding the circuit, avoiding closing the circuit, and avoiding 3 edges coming out of one vertex. Okay, that's important because we'll end up not being able to complete the circuit if we have 3 coming out of one. Let me word this better. We want to avoid closing the circuit early. And the rest. Okay. So we want to keep doing this, avoiding closing the circuit early and avoiding 3 edges coming out of one vertex. So the reason I'm reminded of it here is because if we pick the next shortest one, that's going to be this one, right? And then we have 3 coming out of B, and then we won't be able to complete the circuit appropriately. So our next choice would be 5 here, but that's going to close the circuit too early, right? That's closing, we would have a circuit already, but we don't have A in there. So that one can't be it. So the next smallest is 6, and that's fine, right? We only have 2 coming out of D, and we're not closing the circuit. So finally, if we want to close the circuit, the next smallest one is 4, but then it's not going to be a circuit, right? We're going to have this circuit with this edge coming off of it. So we have to go this way with 8. We also just can't have 3 coming out of B anyway. Okay. So this is our circuit. It doesn't actually matter which one we start at now. We didn't pick a starting vertex, but we could just write it as B, D, A, C, B, or any combination there. And so our weights are 3 plus 6 plus 8 plus 3. Whoops. Oh, my pen stopped working. Good thing we're almost done. I'll use my mouse for now. So 3 plus 6 is 9. Plus 8 is 17. Plus 3 is 21. So it's definitely not the best circuit that we found. Actually, that doesn't make any sense. What do we do wrong here? Oh, 17 plus 3 is 20, not 21. Okay, so it's not the most optimal path. Again, we're just finding an efficient path. Really, the only way we can guarantee finding the optimal path is with the brute force algorithm. But that one's too hard for, most graphs, at least to do by hand. What really ends up happening is, in the real world, when we're looking at this stuff, most of this stuff is done on the computers. And with computers, it's easy to brute force it because the computer can easily deal with like millions of different data points at one time. So you could just have it find the millions of Hamiltonian paths that you need and then find all the weights and then just take the smallest one. So it's a lot easier to do with computers. By hands, we're limited to really doing it when with like 4 vertices or less, which isn't very many, right? So that's pretty much it for this chapter. There's 2 more definitions though. So let me leave you with those. I'll have to type them here since my pen stopped working. It does that sometimes. Luckily, it did it at the end here. Let me grab. Does not want to let me type, it looks like. There we go. All right. Wait, let's make it way bigger than that. Okay, so definition. Maybe a bit smaller. And efficient algorithm. Whoops. An efficient algorithm is an algorithm for which the number of steps needed to carry it out grows in proportion to the size of the input of the problem. Okay. So an efficient algorithm, just underline that, is an algorithm for which the number of steps needed to carry it out grows in proportion to the size of the input of the problem. So that means if we have 4 vertices and this takes 4 steps, let's say, then if it has 6 vertices, it should have a proportional number of steps. Like, for example, if let's say it has 2 vertices, then there's 1 step, or 2 steps. If there's 3 vertices, then there's 4 steps. So now it's grown by 2. For 1 vertex, made it grow by 2. If there's 4 vertices, now there are I can't remember what I said. Let's write it down. Let's say 2 vertices. Okay, vertices, steps. 2 vertices, let's say there's 4 steps. 3 vertices, there are 8 steps. 4 vertices, there are 16 steps, and so on. It's growing proportionally because here it's doubling every time. Every time the vertices go up by 1, the number of steps double. So I wanted to illustrate it this way because you don't necessarily need the number of steps to go up by the same amount as the number of vertices as long as it's proportional. So here, because it's doubling every time, for every 1 vertex it doubles, it is proportional. Okay, so you don't need to worry too much about this. It's just throwing a couple things in about algorithms at the end here. We care about efficient algorithms because we need to know, usually we're doing these in computers, we need to know how many steps it's going to take the computer to do so that we know to limit our number of inputs. For example, like if we know the computer can only handle like 1 billion steps or something, we would need to know that the graph we put in can only have like 500 million vertices or something like that. Might seem like big numbers, but it's really something that could come into play. The approximate algorithm, I won't write it out here. It's in the book though, but you don't have to worry about it. But the approximate algorithm is any algorithm for which the number of steps needed to carry it out grows in proportion to the size of the input of the problem. So that's very similar to this definition. But there's no known algorithm that is efficient and produces the optimal solution. Okay. So basically, it's an efficient algorithm, but we know it's not going to produce the optimal solution, which was the last 3 that we saw there, right? The nearest neighbor and the cheapest link, they were efficient algorithms, but they're still approximate algorithms because we know that they're not going to produce the optimal solution every time because we saw that they didn't, right? The brute force algorithm, on the other hand, I believe is not an efficient algorithm at all because the number of steps could grow by a lot very quickly. But it does produce the optimal solution. Okay, so there's some trade-offs. And oftentimes we often have to settle for approximate rather than exact because of these trade-offs. Okay. So that's it for chapter 6. The test for chapter 6 will it'll be a little smaller than most of the tests, I think, because there's not a ton of material in this chapter, but it will cover all of chapter 6. Like it'll be shorter than the chapter 2 test, for example. That one will probably be the biggest one. So definitely prepare for that. You'll have plenty of homework problems to work on, and just make sure you know how to find the Hamiltonian paths, like how to do the cheapest link, nearest neighbor, and brute force algorithms for the small number of vertices at least. What a Hamilton path is, what an Euler path is, how to find the Euler paths, how we know if we have the Euler circuits or paths, how to do these algorithms back from 6.2, Kruskal's algorithm for finding the minimum spanning tree, and then just all the basic definitions from chapter 1. Okay. If you have any questions on it, let me know. And then after the test, I will, depending on how this falls anyway, either after or before the test, I'll see you on the next one for chapter 2. So we're going to move on from graph theory. We're going to be completely done with graph theory and move into a different subject, statistics. Okay, so that's how this class is. Statistics will be a fresh start from graph theory. You won't need to remember any of this stuff for that. It's completely, all the chapters are going to be completely on their own. So it's not going to build off each chapter like math typically does. It's going to be a completely new topic from scratch. Okay, so I'll see you guys next time for statistics. And thank you for watching this video and all of the chapter 6 videos.